We on? Cramers Rule, brought to you by Group 9. In case some of you are trying to forget the horrors of Maths 141, here is a little introduction on Cramers Rule. Cramers Rule is named after this guy, Gabriel Cramer, and is mainly a mathematical tool used to solve system of equations through the use of the determinant. The mathematical advantage of Cramers Rule is able to solve complex systems of linear equations, like the one present with ease. It is a fast, easier way compared to other methods. And just like that, we have our answer. Cramers Rule is advantageous in real-world application, as Cramers Rule is widely used in engineering, mainly electrical or mechatronic. For example, by using Cramers Rule with nodal analysis, engineers are able to determine electrical features from intricate circuits. Cramers Rule also branches out of engineering and is useful in things like integer programming and macroeconomic application.
Let's say we have these equations and we want to find out what the variables are. One way we can do this is using the Cramers rule. Firstly, we take the coefficients from the equation and create an augmented matrix. Next, we find the determinant. We find the determinant by simply using this formula and substituting. So using the formula, we get our minors and we can calculate the determinant. As you can see, it doesn't equal 0 and we can find a solution. So how do we use Cramers rule? Well, we take the solutions column and replace it with the column of the variable we wish to find. Then we calculate the determinant. As you can see for x, the x column was replaced with the solutions column and we got this coefficient matrix. Then we calculate the determinant like before. Simply repeat the same process for y and get the determinant. Similarly, do the same thing for z. So what do we do with the determinants we found? Well, we simply take the determinant we found over the original determinant and we can find the variable.
Now we're going to look at a mechatronics application of Cramers rule. Mechatronics deals mostly with control systems, using different sensors to control what a machine does. In this case, we want to control some smart blinds that close when the light is at a specific brightness. This circuit uses a photosensor that will output 3.3 volts when the blinds need to be shut. So we need to find the voltage V2 to know what input voltage to program into a microcontroller. The easiest way to do this is with nodal analysis, using the fact that the sum of currents entering a node equals the currents leaving the node. After deriving these equations, we can rewrite the currents in terms of voltage and resistance. After a bit of manipulation, we arrive at the following formulas, noticing now we have two equations and two unknowns. To solve for V1 and V2 easily, we put our equations into matrix form and calculate our determinant. Then we simply put both together to find our node voltages V1 and V2. So now we know that an input voltage of 8.87 volts will be the boundary condition to close the blinds.
Wonder what are the real world applications of them? Well, the answer is the op-amp. So what is an op-amp? An op-amp is a unit which amplifies the output voltage and hence the power significantly. By connecting it with an electronic circuit within devices, any noise or light or any other medium can be amplified greatly. So where might you have used this device? It had its applications in the early analog computers, nowadays used in many modern consumer, industrial and scientific devices, and is mainly used for amplifying signals and noises. So, for example, a guitar effects foot pedal, a boombox, and a barcode scanner. The op-amp depends significantly on node analysis as the unit is made out of a large number of nodes. Therefore, precise calculations of voltage across each node is needed. Also, node analysis is great for finding where faults are in devices such as op-amp. And what better way than using node analysis and hence Cramers rule in tandem to solve for the large amount of equations to rise out the circuit.